Hey there, science fans! Have you ever wondered how engineers design things to last? It's all about reliability. Think about it. Your phone, your car, even a simple light bulb. They all need to work when you need them. Reliability is like a measure of trust in our gadgets and gizmos. It tells us how likely something is to perform its job without failing. And in a world increasingly reliant on technology, this is more important than ever. We rely on complex systems every day, from transportation and communication networks to medical devices and power grids. When these systems fail, the consequences can be inconvenient, costly, or even dangerous. That's why understanding and improving reliability is crucial for a safer, more efficient future. So, next time you flip a switch or tap a screen, remember, there's a whole lot of science behind making sure things work when they should. Now let's dive into a specific type of system engineers deal with all the time: series systems. Imagine a simple chain. What happens if just one link breaks? The whole thing falls apart, right? That's how a series system works. Each part is like a link in the chain, and they all have to function perfectly for the system to work. If even one component fails, the entire system fails. Think about an old-fashioned string of Christmas lights. If one bulb burns out, the whole string goes dark. That's a series system in action. Series systems are everywhere, from simple circuits in your toaster to complex assemblies in airplanes. Understanding how these systems work and how to make them more reliable is a big deal for engineers and scientists. Now, figuring out the reliability of series systems seems simple, right? You might think it's just a matter of testing each component and seeing what fails first. Just test everything and see what breaks. Easy, right? Well, not so fast. In the real world, we often deal with something called censored data, which complicates things quite a bit. Imagine you're testing a bunch of light bulbs to see how long they last. You start the experiment and wait. Some might burn out quickly, within a few hours or days. Others might keep shining for days, weeks, or even longer. But what about the bulbs that are still working when you have to stop the experiment? You can't wait forever. That's right. Their failure times are a mystery. We don't know when they will fail. This is called right-censored data, because we only know the failure happened sometime after our observation period ended. To make things even trickier, we might also have masked data, adding another layer of complexity. This is where we know a failure occurred, but we don't know exactly which component in the series system gave out. It's hidden from us. It's like knowing a link in the chain broke, but not being able to tell which one. The failure is there, but its exact location is unknown. So, how do we estimate reliability with all this missing information? It seems like an impossible task. That's where some clever math comes in. Advanced statistical methods and models help us make sense of the incomplete data and estimate reliability accurately. Section 4. Cracking the code, maximum likelihood estimation to the rescue. Don't worry, everyone. We have a powerful tool to solve this mystery. Maximum likelihood estimation, or MLE for short. Think of MLE as a detective trying to solve a case with only partial clues. The detective gathers all the available evidence and uses logic to find the most likely scenario that explains the observed facts. In our reliability case, the evidence is our censored and masked data. MLE uses this data along with some mathematical models to find the most likely values for the unknown failure times and component reliabilities. It's like putting together a puzzle with some pieces missing. MLE helps us fill in the gaps and get a clearer picture of the system's reliability, even with incomplete information. Section 5. Eureka, what we learned about reliability. So what did we discover using MLE to study series systems with censored data? Well, it turns out MLE is a pretty powerful tool. First, we found that MLE can provide accurate estimates of component reliability, even when we have a lot of censored or masked data. This is crucial because in real-world scenarios, data is often incomplete or obscured. That's great news because it means we can still learn a lot about system reliability, even with limited information. Second, we learned that the more data we have, the better our estimates become. This is because more data points help to refine our models and reduce uncertainty. It's like solving a puzzle. The more pieces we have, the clearer the picture gets. Each piece of data adds to our understanding, making the overall image more precise. This highlights the importance of collecting as much data as possible during testing. Comprehensive data collection is key to accurate reliability assessments. However, we also discovered that MLE can struggle when certain components are extremely reliable. If a component almost never fails, it's hard to estimate its reliability accurately, even with MLE. This is because the lack of failure data makes it challenging to model the component's behavior. It's like trying to study something that's invisible. Without enough failure instances, the reliability of such components remains elusive. Section 6. From factories to your living room, real-world reliability. Now, you might be wondering, why should I care about the reliability of series systems? Well, it affects us all in countless ways. Let's start with manufacturing. Imagine a factory production line. It's basically a giant series system. If one machine breaks down, the whole line can grind to a halt, costing time and money. Reliability engineering helps keep those factories humming along, ensuring that each component works as intended. But it's not just about factories. Think about your car. It's a complex system with thousands of parts, many arranged in series. Reliability engineering ensures those parts work together seamlessly, keeping you safe on the road. Even your smartphone, with its intricate circuits and components, relies on the principles of reliability engineering. From the battery to the touchscreen, every part needs to function flawlessly for the phone to work as expected. Reliability engineering impacts the design, manufacture, and maintenance of countless products we use every day, making them safer, more efficient, and longer lasting. Whether it's the appliances in your kitchen, the gadgets in your pocket, or the vehicles you drive, reliability engineering is at the heart of it all. It ensures that our daily lives run smoothly, reducing the chances of unexpected failures and inconveniences. By focusing on reliability, engineers can predict potential issues before they arise, creating products that stand the test of time. So, the next time you use any device or machine, remember the unseen work of reliability engineering that makes it all possible. Section 7. The future is reliable. Embracing a more dependable world. As we rely more and more on technology, understanding and improving reliability becomes increasingly vital. From self-driving cars to complex medical devices, the systems we create are becoming more intricate and interconnected. The research we've discussed today, using MLE to understand series systems, is just one piece of the puzzle. Scientists and engineers are constantly working on new methods to design, test, and maintain systems that are more reliable and resilient. By embracing the principles of reliability engineering, we can create a future where technology works seamlessly, empowering us to live safer, healthier, and more productive lives. So the next time you marvel at a technological wonder, remember the unsung heroes, the reliability engineers working tirelessly behind the scenes to make sure it works, day in and day out.